When you're at the grocery store, you're often faced with a choice, which line do I want to wait in? Clearly, we want to get out of there as quickly as possible, so we're trying to pick a line that moves fast. And maybe we can say, well, there's fewer people in this line, or the people in this line have more things in their cart. And we can use those clues when we're there to decide which is the better line. But if we're just looking at a data set of wait times, how would we use a numerical value to help us decide which line is going to move more quickly, or which line is the better line? Line 1 has 6 wait times, ranging from 4 to 7, with an average value in the center of about 6. And line 2 has only 5 wait times, ranging from 2 minutes all the way up to 10 minutes. But ironically, they both have the exact same average wait time. They both calculate an arithmetic mean of 6 minutes. So looking at the average wait time would not be the best way in this case to choose which line, because it doesn't give us any pertinent information. That leads us to a discussion about spread. Now, on average, people in line 1 wait 6 minutes. Some people only waited 4 minutes, which is a couple minutes less than the average. But in line 2, the average still being 6 minutes, some people only went 2 minutes in line. That's less 4 minutes. Now, if you're a gambler, you're probably going to pick line 2 because the smallest wait time is impressive. But what if that person just forgot their wallet? That's not a good representation, so we don't want to just use the minimum. But maybe we do want to look at the spread of our data. Line 1, the wait times are more consistent. So saying you'll wait about 6 minutes, that's pretty accurate. But in line 2, the spread goes from 2 all the way to 10. The data values are pretty far apart. If I tell you that you're going to wait on average 6 minutes, but it ends up taking you 10 minutes, you would think maybe I didn't give you a very good indication of how long to wait. One measure of spread that we can use to describe a data set is the range. The range can be written as an interval where we give a minimum value and then span up to the maximum value. So for line 1, our range was 4 to 7. And in line 2, our range was 2 to 10. To calculate the range, we would just do the maximum value minus the minimum value. So for line 1, our range interval 4 to 7 results in a range calculation of 3. In line 2, our range interval is 10 to 2, which results in a range calculation of 8. So the data in line 2 is far more spread out, clearly, than it is in line 1. So if you're looking for a consistent line, maybe you want to wait in line 1. Range is a good way to talk about spread of data, but often we use another calculation called the standard deviation. Standard deviation is a calculation that talks about how spread out the data is. Let's illustrate this with our waiting in line example. If we know that the mean waiting time is 5 minutes, and we're told the standard deviation is 2 minutes, that means that you could wait 2 minutes longer or 2 minutes less than the mean. So one standard deviation away from the mean ranges from 3 to 7 minutes. We use this calculation as a way to talk about what is close and what is far from the mean. Close and far are subjective terms. Some people think that a mile is close, some people think a mile is far, right? If you have to walk it, that's far. If you get to drive it, it's close. Very subjective. So we standardize what we mean by close and far by using the standard deviation. It's a calculation that we'll get into in just a moment, but for now I want to point out the fact that we're talking about 2 minutes being considered pretty close to the mean. If we were to do 2 standard deviations away from the mean, that's a little bit further. I'm still going to call that close-ish. 2 standard deviations in this case would be 4 minutes above or 4 minutes below the mean. We can look at 2 people who waited in line, Rosa and Ben. Rosa waits 7 minutes, Ben waits 1 minute, and if we look at where they are on the number line, we can see that Rosa is 1 standard deviation away from the mean, Ben is 2 standard deviations away from the mean. So Rosa we would call close, and Ben we would call right on the boundary of being far away from the mean. Standard deviation is one of the measures that we use to talk about the variance or spread of a data set. Variance is another calculation, and it's something that you pick up along the way of calculating the standard deviation. So we have two things to talk about here, variance and standard deviation. The notation for variance is s squared if we're talking about a sample. If we're not talking about a sample, then variance for a population, we're going to use our Greek letters sigma squared. So we have sample variance, s squared, population variance, sigma squared. And then for standard deviation, we also have separate notations. For population, our standard deviation, again, is the Greek letter sigma. Standard deviation and variance, they look very similar in their notation, but remember variance has the square, the exponent on it. Standard deviation does not. So then for sample standard deviation, our notation is just S. All right, I do have the formulas on the screen to calculate standard deviation, no matter if we're talking about a sample or a population. The formulas look pretty similar, but there is a key difference. In the sample calculation, we're looking at a formula that involves x bar, the average of our sample. In the population standard deviation, we use mu, the average of our population. So we have to be very careful here. Make sure that when we're calculating standard deviation or variance, we know if we're dealing with a sample or a population. That way we can use the appropriate measure of center for our calculation. Let's run through an example of calculating a standard deviation on a sample, and we're going to do this twice. We're going to do it the first time where we ignore this frequency column, and we just pretend like each of the data values in our data set appears exactly once. So we have 9, 9.5, 10, 10.5, 11, 11.5. That's a total of 6 values. In order to do this standard deviation for a sample, we need to first calculate the deviation from the mean. That's exactly what this deviation column says. It says take your data value, anything from the X data column, and subtract the mean from it. Well, that means we have to calculate the mean first. So let's go ahead and calculate the average here, the mean, for our data values. We can throw our data values into a calculator to calculate the average, or we can use symmetry to our advantage. We know that we have 6 values. They're equally spread apart by a half a value or a half a unit from one value to the next. I know the center is going to be between 10 and 10.5. Our mean is 10.25. So again, you can verify that on a calculator. Next, we can use that mean to create our deviations. So for each data value, we need to subtract the mean. Each of these deviations is going to result in a single number, and it might be positive, it might be negative, but that's okay. Let's go ahead and evaluate each of these differences, each of these deviations. All right, so we have all of our deviations. Notice that the values that are less than the mean, like 9, 9.5, and 10, those all have negative deviations. The values that are above the mean, 10.5, 11, 11.5, those all have positive deviations. If we were to add these together, just adding straight down that deviation column, we would get 0. And 0 is not very helpful mathematically. So what we need to do is create a positive value from each of these deviations, and that's where the square comes into play. We'll take each deviation and square it. That's going to be the deviation squared column. So taking each of our deviations and squaring them, so negative 1.25 quantity squared, we get a positive number, 1.5625. We repeat that for all of the rows in our table. Now we have our square deviations. If we're ignoring frequency, then this last column in our table is also obsolete. All we need to do now is add up all of our deviations. In our formula, that is exactly what the numerator inside of the square root is telling us to do. This big backwards looking e, or not backwards, but funny looking e, it's called sigma. It's capital sigma, and it tells you to sum all of the values that look like the square deviations. So now we're going to add down our deviation column. Adding our square deviations, I get a total of 4.375. So that is what we're going to put in the numerator of our sample calculation, so our sample standard deviation calculation. In the denominator, I need n, which is the number of values in my data set, minus 1. Here we have 6 values. We'll subtract 1 from that. 6 minus 1, that's our denominator. I'm going to go ahead and just write 5 there. And then we need to square root that fraction. So at this point, we pop it into our calculator, type in the square root of the fraction 4.375 divided by 5, and we get our standard deviation for the sample to be about 0.9354. I'll keep 4 digits here. So if we're looking at a data set where each of the data values appear exactly once, we can use this process to calculate the standard deviation. If, however, we're looking at a frequency table, we need to include the 2 columns that I've crossed out. So let's try that example. Our data set this time is not just 6 values. We need to add all of our frequencies to count how many data values are in our data set. I find that we have 20. So adding down our frequency, we can see that there are 20 values in our data set. We need to calculate the mean so that we can calculate our deviations just like we did in our last example. But recall that to calculate the mean, I'm going to have to include the frequency here. So I have 9 times 1, 9.5 times 2, 10 times 4, 10.5 times 4, 11 times 6, 11.5 times 3. I need to add all of those up and then divide by 20, since we have 20 data values. That will give me the sample mean of 10.525. Next, we're going to calculate the deviations for each data value. So we'll take the data value, 9, and subtract the sample mean, 10.525, and we're going to do that for all of the data values. For the 9s, we are 1.525 below the mean, so we have a negative number. For 9.5, for the 10s, for the 10.5s, for the 11s, and for the 11.5s. So we have all of our deviations. Now we're ready to square those deviations. So here I've taken each deviation, squared it, and wrote the result down in the square deviation column. And now we're going to bring the frequencies back in. So we know what the deviation looks like for each data value. We know what the square deviation looks like for each data value. But we need to give the weight appropriate for the frequency. So we're going to multiply the frequency for each data value to its square deviation. So frequency times our square deviation. And we're just reading values here from our table. So I'll multiply my frequency of 1 to my square deviation. Next, the frequency of 2 to that corresponding square deviation. The frequency of 4 here. Another 4. Frequency of 6. And last one is a frequency of 3. Now, because we're looking at a frequency table where the frequency for each data value is different from 1, I needed to do this frequency times square deviation for the numerator in my standard deviation calculation. So this is a little bit different than the last example. I still need to add all of those up. I see that large sigma saying to add up all of my frequency times square deviation. So we're going to add everything in this last column. Now with the 4 digits that I've kept in most of my values, with the exception of the 10.5 data value, I am rounding here and we need to be a little bit careful, but just to demonstrate how to use this table and keeping it concise enough to fit, I'm only keeping 4 digits to the right of the decimal. And when I add my frequency times square deviation column, I'm getting 9.7371 approximately, right? This is a little bit off because of rounding, but it'll get us to the point. That is our numerator. That's what we're going to put inside of the square root in the numerator for our standard deviation calculation. So we will draw our big square root. We have our numerator of 9.7371. And then again, we're going to divide by the number of values minus 1. We know in this frequency table there were a total of 20 values, so we will have 20 minus 1, or 19, as our denominator. And our very last step is to evaluate that in a calculator. So the square root of the fraction 9.7371 divided by 19. We get a standard deviation that is about 0.7159 if I round to the 4th decimal place. So we can calculate standard deviation by hand, whether or not we're looking at a set of raw data or a frequency table, just by creating these columns and building the formula for standard deviation as we go. But also we can do these calculations in our calculator. If we use that data table and the one variable statistic calculation, or the or the frequency table calculation, we can easily get standard deviation from our calculator. So we won't do it by hand in practice, but it's good to understand how these numbers come from our calculator, what the calculator is actually doing.